Okay, hi, welcome everybody. Welcome to the next to last TCS Plus of this fall. Um, Today's speaker is Sanjam Garg. We are very happy that he agreed to talk about this very exciting progress in cryptography. Um, we have several new groups joining this time, so I hope it will all go smoothly. We also have tiny bit of technical trouble with muting participants remotely. So please make sure that you're all muted. Um, Let me tell you a few things about Sanjam before we introduce the participants. Sanjam graduated from UCLA under Raphael Ostrovsky and Amit Sahai. His work introduced proposal for a candidate multilinear map constructions. This thing has been open for many, many years. It's a wonderful breakthrough, and he's going to tell us today about an application of that to another wonderful topic of obfuscation. Currently, he's at IBM Watson, not far from me, under Joseph Raviv Fellowship. So some new groups are coming, joining us today from Tel Aviv. I see Weizmann is the first time we have groups, I believe, from Israel. I hope technically it all goes smoothly. And as usual, I welcome all of you to ask questions. That's the purpose of TCS Plus. Like, let's try to make it interactive. So whenever you feel like, just unmute the microphone and ask a question. I should have introduced Thomas. Thomas Vidic is with me here helping make this whole happen, despite all the technical troubles Google is trying to cause. So Thomas, I'll let you introduce the groups, and then we'll start with the talk.
All right. So let me quickly go around the table and try to familiarize ourselves with everyone. So we have Arno from, I'm not sure where, Arno.
Hello.
Hi, welcome.
So I'm from TU Darmstadt in Germany.
All right. Well, thanks for joining. Then we have Bill from Caltech. Hey guys. Daniel from University of Maryland, and a big group there. Welcome everyone. Then we have Job from NYU, and a group there as well. Then we have Kate Golappakrishnan, welcome. Then we have me here from, so the camera is pointing to the ceiling. Someone's hiding below the camera, I hope. Well, welcome.
Yeah, it's a UCSD group.
Okay, me here from UCSD. Then we have a group from Tel Aviv, welcome.
Hello.
And finally, a huge group from Weizmann, who's doing things the correct way with, we can see nice drinks and appetizers here, so we hope you enjoy the talk. All right, with that I'll return the...
Okay, thanks. I also forgot to mention the next speaker. So in 2 weeks, we'll have David Stoyer, and I believe he'll be telling us about, do you remember correctly, standard formulations, is that it?
I think so, yes.
Okay, good. So, okay, so you'll hear about this. This will be the last talk, and we'll resume in the spring, I hope. It's going to be 2 p.m., slightly unusual time. Okay, so kept you all waiting. Let's start. So, Sanjam, thanks for agreeing to speak today, and please go ahead.
Hi, can everybody hear me?
I can hear you.
Yeah.
Okay, great. So thanks for Oded and Thomas for inviting me. I'm really glad to be here giving the talk. I want to stress again what Oded said. Please feel free to interrupt and ask any questions. That's the only kind of feedback that I have here with respect to what's going on. And also, if you don't, it's not a question, but if you think that there's a comment that you would like to make, please feel free to interrupt and ask, state your comment.
Sanjam, we cannot see your slides. I don't know if it's just us, but are we supposed to see your slides now?
Yes,
You're supposed. There was an issue here, but it should resolve, I hope. Let's give it a minute.
Thanks.
Yeah. Okay, okay. It's back here. If anyone, is everybody good? Yeah. So as far as I'm concerned, it seems all perfect, so we can go on. Let's hope it doesn't repeat.
So should I go on, or should I wait?
I think you can go ahead. Unless someone starts waving, we'll let you know if there's an issue.
Okay, sounds good. So today I'm going to talk about indistinguishable obfuscation and applications. This is joint work with Craig Gentry, Shai Halevi, Mariana Rekova, Amit Sahai, and Brent Waters. Okay. The talk is roughly going to be partitioned into two parts. In the first part, I'll tell you what is obfuscation and what is it useful for. So this will be very introductory. And in the second part, I'll get to the more technical part of the talk, where I'll tell you how we actually construct obfuscation. And hopefully by the end of it, I'll have described at least our construction. Okay, let me start with the first part. So the goal of software obfuscation is to make computer programs unintelligible while preserving their functionality. What unintelligibility means is, in a formal sense, is delicate to define, and we'll see later what it means. But for now, I want you to think about the following scenario. We have a party, Alice, and she holds a program P. Think of it in your favorite programming language, C, Java, or what have you. And she would like to give an obfuscated version of this program to Bob. So she would like to somehow obfuscate it and give it to Bob. And the requirement is that from Bob's perspective, running the obfuscated program on his computer should be just be the same as running the program P. Okay, so he should not notice any differences with respect to running the program, except a potential slowdown, but beside the input-output behavior should remain identical. Okay, and the second requirement from the Alice's perspective is that this obfuscated program should be unintelligible, or it should at least hide the intricate details about how the program P works. Again, we'll see later what this means in a formal sense, but this is the intuitive notion I want you to keep in mind. Okay, obfuscation has many conceptual applications. Let me start with a very simple and very important conceptual application that applies to the task of protecting intellectual property. So imagine Microsoft Office. It's a very widely used software. But Microsoft also suffers from lots of problems of piracy when distributing the software Office for consumers. Obfuscation provides a solution to this problem, and the solution would be for Microsoft to, instead of giving Office in its current form, to give Office in its obfuscated form to consumers. Now notice that when Office is in its obfuscated form, from the consumer's perspective, his user experience does not change at all, because the experience that he runs in when running obfuscated version of Office is identical to what he gets when he runs the unobfuscated version. Again, stressing again the speed change that might occur. But it makes a huge difference from the perspective of Microsoft. The difference is that given the obfuscated version of Office, a potential malicious user or a hacker cannot figure out how Office actually works and generate pirated versions of the software. So it will significantly help in bringing down piracy of the software, which is very important from a business perspective for Microsoft. Another example, a sort of a conceptual example of obfuscation lies in the task of patching software securely. Okay, so this is a slightly less known example, and I would like to bring it out. So consider, for example, any software package, for example, Norton. Many of you might have it installed on your computers. Let's say one fine day, or maybe a sad day, Norton discovers a bug in their software, and at this point they would really like to release a patch to fix this bug. Okay, so let's say Norton immediately, as soon as they discovered this, they have an active team of researchers trying to find bugs in their software, and as soon as they find a bug, they release a patch to fix this bug. Now an attacker who just sees the bug can reverse engineer this bug and find out what the bug was. So it can look at the patch and find out what the bug was. And knowing what the bug was, it can go and attack the unpatched machines. So if Norton releases a patch today, it's unlikely that every machine on the internet will get patched the same very day. So the attacker who is fast enough can figure out the bug from the patch and then attack the unpatched machine. Okay, and solution provides like sort of the only kind of theoretically sound solution to this problem. The solution would be for Norton to, instead of generating the patch, generate an obfuscated version of the patch. So instead of generating the patch in the clear form, it generates an obfuscated version. And then an adversary who has access to the obfuscated patch cannot figure out the bug. Okay. Of course, it could look at the do detailed analysis of the software and try to figure out what the bug was. But just given the patch, he cannot do that. And once large-scale deployment of this patch has happened, maybe potentially after a week or even a month, depending on the software, Norton could release a more efficient version of the unobfuscated patch. So at this point, there are no unpatched machines in the system. So even if adversary learns what the bug was, it doesn't affect the security of the software. So at this point, Norton could release an unobfuscated version of the patch. Okay. So these are the conceptual applications I wanted to talk about. Any questions? Okay, I'll move on. So what does the state of the art offer for obfuscation? So, these are really important problems that we have. The intellectual property protection and there are many more besides the ones I mentioned. But an important question is, well, what does the state of the art offer? And yes, a lot of effort is made in trying to achieve obfuscation, but most of it follows the principle of security via obscurity. So what does this mean? So there are two kinds of ways of going about obfuscation. The first one relies on a sort of approach of human ingenuity, and the goal is that the person who actually sits down to write the program makes sure that the program is difficult enough to understand. So he sits down, he makes a lot of effort in ensuring that if you spent a lot of time on figuring out what the program does, it would not be easy. For example, this code snippet that I have here has been taken from, it's a winning entry from International C Code Obfuscation Contest, and the person writing the code, so this is an actual program that calculates the square root of a given number. But the person who wrote the code made a lot of effort in making sure that nobody could understand what this code does. And this is where, but if you were to spend, say, a week on trying to figure out how this code works, you probably will be able to figure things out. Another more systematic way of obfuscating is to use various security tools such as the Enigma Protector, the Crypto Obfuscator, and many more. So let me stress that the Crypto Obfuscator has nothing to do with crypto, and how these tools broadly work is by renaming variable names, renaming function names, and changing how function calls are being made. So all these tools are making the task of, again, the person who's trying to reverse engineer really difficult. But the bottom line is that these tools and the programmer himself trying to do it, or whether he uses a software solution, they only make the task of reverse engineering time-consuming, but not impossible. So if you were to spend a significant amount of time, possibly around, say, a week, then you would be able to break this. On the other hand, in this work, we would like to construct a solution for all circuits that doesn't have this problem, where we are giving a solution which is sound theoretically, achieving some well-specified notion of security, and it's cryptographically secure, so its security is based on certain hardness or certain computational assumption. I want to stress that the key technical tool that has helped in realizing this goal has been multilinear maps that was realized recently in a joint work with Craig Gentry in Shirley. So I'm not going to talk much about it except when I get to the technical part, but this is the key tool that helped us in making obfuscation possible. There are a bunch of important points that I want to make. The first is that the construction that we have is based on a complex and a new, but still very reasonable computational assumption. So we'll get into details of what this assumption looks like later. But this is a huge leap from the state of the art, where obfuscation solutions that we know in the literature, realizing any definition of security, regardless of whatever definition you want to consider, were limited to very special families of functions, such as point function. So we had some other families as well, but probably the most well-studied family is for point functions. I want to stress that before this work, we didn't even know any heuristics for obfuscation. So this is a very subtle but an important point to make, because what I want to say is that any construction that existed in the literature or was used in practice by anybody to do any kind of obfuscation was known to be broken. So we had actual attacks to break them. It's not that we didn't have attacks and now we have a scheme which is provably secure and well-defined. All the schemes before had attacks, and we knew concrete attacks on them, and now we have a construction that cannot be broken as long as you can't break the computational assumption that we put forth. Any questions? Okay. Okay, so I told you some of the conceptual applications of obfuscation. Now I want to move on and tell you a little bit about some of the cryptographic applications. So one very well-studied cryptographic application is functional encryption. Has sort of become like the flagship application for obfuscation. The seed for this notion goes back to the early work of Shamir from 1984. Since then, it has been refined and many further generalizations have been given. And what we stand at now is this very general notion of functional encryption, which I'm going to describe next. So the idea is very simple. There are a bunch of users. So we have Bob and Alice, and we have a key authority. Okay. What the key authority does is generates a public key and a master secret key. It publishes the public key, and it uses the master secret keys to issue secret keys for the users in the system. So that's like the big secret key that he has, and he's going to issue secret keys for user-specific secret keys. And in functional encryption, each secret key for each user is associated with a specified function. Okay, so we have the first user. Let's say he gets a secret key corresponding to a function f1. The second user gets a secret key corresponding to some function f2. So these are their individual secret keys. At this point, the secret key authority goes away, and its going away has been done to signify that it doesn't interact with anybody in the system anymore. Okay, so once it gives the secret key, it has no more role to play in the system. And let's say a user comes along. So this user that comes along, let's say he would like to encrypt a message of his choice. He uses the public key, generates a ciphertext, the message being X and the encryption of X being the ciphertext. At this point, the functionality of the scheme requires that if the first user wanted to decrypt the ciphertext using a secret key, he should be able to obtain f1 of X, and if the second user was trying to decrypt, he should be able to obtain f2 of X. The security requires that they shouldn't be able to achieve anything more. So the first user should not be able to learn anything more than f1 of X, and the second user should not be able to learn anything more than f2 of X. By the way, I've just drawn two users here. There could be arbitrary polynomial number of users. And furthermore, the security requirement is required to hold even when arbitrary polynomial number of users were to collude together. So if, for example, the two users in the picture were to collude together, they jointly cannot learn anything more than f1 of X and f2 of X. Okay. So if there are arbitrary number of colluding parties, they shouldn't be learn anything more than what can be jointly learned from their outputs. Is that clear? Any questions?
I missed that. Maybe you mentioned also this. You say contrary to obfuscation, this was already known. You're citing.
No, I didn't mention the result yet. I was just mentioning the primitive.
Oh, sorry. Okay. All right.
So this is a very well-studied primitive, and what was known in this context was that you could realize functional encryption, this notion that I just described, in two settings. One, if you are willing to restrict yourself to the class of functions for which secret keys could be provided. If you are willing to restrict yourself to functions that were described by inner product, then you could do it. Or if you are willing to restrict yourself to a limited setting where you are only providing a single secret key, or more generally a bounded number of secret keys. Okay, you could realize this primitive in those settings. In this work, it's a part of this work itself. We actually realize this notion of functional encryption, which is the best of the both worlds. So you can the functions can be associated with arbitrary functions, and secondly, there's no bound on the number of users in the system. So you can have arbitrary number of users in the system with arbitrary collision. Okay, does that answer your question, Oded?
Yes, thanks.
Okay. Okay, so let me move on to the second application. It's a really cool application. It was first proposed by Rudik in 1989. He didn't propose exactly the same thing, but something very similar, and was realized only very recently in a joint work with Gentry, Sahai, and Waters. And the idea here is to rethink, in some sense, encryption itself. Normally, whenever you think of encryption, you're trying to encrypt to a specific party. You might be encrypting, if it's secret key encryption, you're encrypting to someone who holds the same secret key as you do. If you're thinking of public encryption, you're encrypting to someone's public key. Instead, we would like to think of a notion where the encryptor doesn't have a particular recipient in his mind. He's trying to encrypt to a particular statement instead. So there's the statement. He's trying to encrypt his message to the statement. Think of this statement as, for example, a crossword puzzle that appeared in the New York Times, or more generally, any NP statement, for example, any SAT formula. Okay, so it could be any SAT formula. And our encryptor would like to generate a ciphertext corresponding to the statement. I want to stress that the encryptor doesn't know witnesses or anything about the statement. He doesn't even know whether the statement is satisfiable. So for example, he doesn't know whether the crossword puzzle that appeared in the New York Times was bogus. So there was no solution to this problem. He doesn't know if the SAT formula is satisfiable or not. He knows nothing about the statement. He just has a statement he's encrypting. And he doesn't have a recipient in his mind at all. Now imagine that in this encryptor, after generating the ciphertext, he at some point, he's no longer around to answer his questions. Maybe he dies, and along with him, his ciphertext is lost. And another 100 years later, let's say a recipient comes and he claims to know a witness to the statement. So if it was a crossword puzzle, he claims to know a solution to the crossword puzzle. And if the statement was a SAT formula, and he claims to know a satisfying assignment for the SAT formula, then we want that this recipient should be able to use this witness and recover the message that was encrypted originally in polynomial time. Okay? And this is the goal. And the security requirement, I'm sorry, it's kind of hiding underneath the pictures. I'll state that the security requirement is that if the statement is unsatisfiable, what I mean by that is if it was a crossword puzzle and it was bogus and it didn't have a solution, or if the SAT formula doesn't have any satisfying assignment, then semantic security should hold. Then no computationally bounded receiver should be able to tell what the encrypted message was. I want to stress again that at the time of encryption, the encryptor doesn't know whether the statement doesn't even know whether the statement is satisfiable or has a valid address. Is this application clear? Any questions? We can realize this using indistinguishability, using our obfuscation solution. We'll see how it happens later on in the talk. Okay, the final cryptographic application I want to talk about lies to the task of realizing multi-party computation with minimal communication. Okay, so multi-party computation was this really important tool in cryptography introduced by GMW, and I'm going to talk about a specific instance of this problem. So consider, let's say we have 5 parties, and they have certain dollar bid value in their mind, okay, and they want to figure out which guy has the highest bid value. But they don't trust each other, and they don't want to share their bid values with each other. Okay? So they want to figure out who has the highest bid without actually revealing their bids to each other. Okay? All solutions for this is a very well-studied notion in cryptography, and all solutions to this problem still did not achieve a round optimal solution. So the only known solution in the literature that gets a provably round optimal solution was only recently. Well, I mean, I have a 2014 citation because it's appearing in TCC next year. It's a joint work with Gentry, Halevi, and Rykova. It achieves a round optimal solution for the first time. Okay. Any questions? Okay. Okay, there are a lot of applications that have come about. I'm not going to talk about all of them. Any possible primitive that has been studied in cryptography, there is a potential scope for improvement if something was left open. So I would urge you, if you want to study obfuscation, to look at your favorite application and see if you can do something more. I'm not going to talk about these applications anymore. And since it's a TCS plus talk, I want to get to the technical part and get you guys all excited and show you how actually obfuscation works. So hopefully I'll be able to make it clear. But let's get to the technical part and see how things work. But before I do that, I need to tell you about the formal notions of obfuscation and which obfuscation notion are we realizing. Okay? The notion of obfuscation as formally says that an O is an obfuscator. Think of it like an encryption algorithm. It takes a circuit C and outputs an obfuscated circuit OC. So this is a randomized algorithm with secret randomness. It takes circuit C as input and outputs the obfuscation O of C as output. And the requirements are that the obfuscated circuit should compute the same function as the input circuit C. Okay, so this is just the maintaining functionality requirement, as I stated early on the first slide of my talk. Second requirement is that the obfuscated circuit should be at most polynomially larger than the input circuit. You don't want to have the obfuscated circuit run in very slowly and run in exponential time or something like that. You want it to be only polynomially larger than the input circuit C. The third requirement is the unintelligibility requirement, which is actually a bit hard to define, and there are multiple notions for it in the literature. The most natural notion in literature is the one in this original paper of Barak, Goldreich, Impagliazzo, Rudik, Sahai, Wadhan, and Young. And then the most natural notion that they had in their paper is this notion of virtual black box. So this is not going to be the emphasis of the talk, but I still want to mention what this notion intuitively means. This notion intuitively means that if I give you an obfuscation, you cannot learn anything more than what you could have learned given black box oracle access to the function or the circuit that I'm obfuscating. Okay, is that clear? Okay, and unfortunately, in the very same paper where they proposed this notion, Barak et al. Showed that there exists functions for which virtual black box obfuscation is actually impossible. So they showed functions, though a little obscure, for which we cannot realize this notion. Okay. In this talk, we will be more interested in this notion of indistinguishability obfuscation that was also introduced by Barak et al. And this notion suggests that if I give you two circuits C1 and C2 such that they compute the same function. So what I mean by that they compute the same function is that for every input that the circuit gets as input, the output of the two circuits on that input are identical. Okay? Okay. And the obfuscation requirement is that if the two circuits are of roughly the same size, then the obfuscation of the two circuits should be computationally indistinguishable. Note that the requirement of the size is not that important because you can always pad the smaller circuit and make it larger, right? You can always add a bunch of no operation gates in the circuit, and you can bring the two circuits to the same size. I noticed that there's a question. Please. Hello, Danny?
Oh, I think what's happening is that we're getting background noise from one of you. Could everyone make sure that they're muted? Or ask a question if there's actually a question, but otherwise, please mute yourself. We have a few surprise newcomers.
Is there a question? Should I go ahead?
It looks good now.
Okay. Oh.
You should go ahead.
Okay, I'll go ahead. So I'll state it again. So indistinguishability obfuscation allows is a notion of this unintelligibility. You still need the first two requirements of maintaining functionality and the polynomial slowdown, but the additional unintelligibility requirement says that if I'm trying to obfuscate two circuits which realize the same function and are of the same size, then the obfuscation of the two circuits are computationally indistinguishable. And this indistinguishability should hold even if the two circuits, even if I give you the two circuits in the clear. It's easy to see that that this canonicalization can always be done if the obfuscator could run in large amount of time. You could always list all possible circuits that realize this function. So I get as input a circuit C1, let's say, I can look at all possible circuits that realize this function. Okay, I can look among them lexicographically the first one and output that. Now note that if C1 and C2 realize the same function, then both of them will output the same value. On both inputs, this inefficient obfuscator will output the same value. But this canonicalization is inefficient, and we would like to do, what we would like is to have an efficient obfuscator realizing the same.
Sanjam?
Yes.
Yeah, I'm sorry. There's some video trouble, and I think I cannot see your slides, and I think I might not be the only one. I don't know why. I don't know if it's your connection or Google or us. We're trying to get it back, so just
It's actually here. It's back. I don't know about the other groups. I can see you, but
okay.
Yeah, maybe give it a minute. Yeah. So Daniel says they can also see that.
Okay, I got it too. So I lowered the quality from HD to medium.
Yeah.
Maybe we'll stay with that for the remainder of the talk.
Okay.
Sorry. This usually doesn't happen.
Okay. Most people say it's fine, so we should.
Yeah. Please continue now. We can see and
it's fine here. Yeah.
Okay. I'll continue. So let me recap a little bit. So what I told was that there is this notion of indistinguishability obfuscation, and I want to. So what I said was I introduced this notion. This notion was introduced in Barak. I told you guys about this notion. The first question that you guys should be asking is that this notion seems really weak. I'm trying to obfuscate two circuits that realize the same function. Why should something like that be even useful in any setting? And actually, probably the strongest justification was actually provided previously by Goldwasser and Rothblum. And the idea is, take any circuit C. On any input, the circuit C evaluates to some output Cx. And imagine the best possible obfuscation that you can think about for this circuit. Okay, so this let's think about the best possible obfuscation for this circuit. And similarly, we can think about just padding our circuit to the same size. So we have our circuit in the clear. We added a bunch of no-op gates and made it equal to the size of the best possible obfuscation that we can think about. And we perform an indistinguishability obfuscation of the best possible obfuscation and the padded circuit. And these two obfuscations are actually computationally indistinguishable. Now what that means is that you cannot even tell apart this obfuscation from an indistinguishability obfuscation of the best possible obfuscation. In other words, this obfuscation is already as good as the best possible obfuscation. Okay, so what we are achieving is that for any circuit, we're achieving the best that we can hope to achieve. This is a very strong security guarantee that's being provided, and that this is what makes the applications possible.
So, Sanjam, how come it's still weaker than the virtual black box?
Well, the virtual black box's definition is impossible to realize. There are functions which you cannot realize, and there is no function for which this cannot be, for which this is impossible. So that gives a clear difference. But in terms of, but if you were to think about intuitively, then there we're requiring a sort of a very strong simulation-based requirement. Here we're having sort of an indistinguishability-based requirement, which makes it easier to achieve. Does that answer your question?
Yeah, I guess I was trying to figure out what fails in your argument, right? You can take the best obfuscation. You might imagine taking it to be the virtual black box, but that doesn't fall into this framework.
Oh, no. So if circuit C indeed has a virtual black box obfuscation, then this is also a virtual black box. But if circuit C doesn't have a virtual black box obfuscation, then you cannot hope to construct it, right?
Right. And among those that you can construct, you'll be as good as the best of them.
Yes.
Mm-hmm.
Okay.
Thanks.
Any other questions? Okay, so let me move on. So as an example, I want you guys to think about a little bit. This will kind of give you an idea about how to use indistinguishability obfuscation. How can we realize witness encryption from indistinguishability obfuscation? I want you guys to think about it for, I don't know, 1 minute or something like that. And for you, if you don't remember what witness encryption was, I have the slide right there. So the idea was the encryptor wants to encrypt a message M to a statement X, The receiver should be able to decrypt if he has a witness for the statement, and the only security requirement is if the statement X is unsatisfiable, in which case semantic security should hold.
So is it the one where knowing the assignment allows you to decrypt?
Yes.
Okay, so you can imagine like the functionality that takes an assignment, checks if it's correct, and if it actually satisfying the form, and if it does, then it outputs X.
Yes. It outputs the message, right? Not X.
Sorry, the message. Yeah.
Yeah. So exactly, that's exactly correct, and it's very simple once you have indistinguishability obfuscation. The construction is exactly as Udit said. I'm going to obfuscate C of M. It outputs the message M. If it takes a input W, it outputs the message M if W is a valid witness and bought otherwise. Note that the security requirement for witness encryption was that if the statement is false, then semantic security should hold. In this case, if the statement is actually unsatisfiable, then the circuit always outputs bought. I see that some people have lost slides. Is it? Okay, I think
I'm
it's
actually
back
good.
on.
Yeah, I'm good.
Okay. Okay, so if the statement is actually unsatisfiable, then the circuit always outputs bought. Now that means that in the case when the statement is unsatisfiable, the obfuscation is indistinguishable from a circuit that always outputs bought. And so it doesn't even have the message, and therefore we have witness. So this was a very simple example which I wanted to show how indistinguishability obfuscation can be used to realize something as powerful as witness encryption. Okay, so next I want to move on to the most technical part of the talk, which is realizing obfuscation. So this is going to happen in two steps. In the first step, we realize indistinguishability obfuscation for shallow circuits, in NC1 or log depth circuits. This construction is what relies on multilinear maps, and the security for this part relies on a complex new assumption. And in the second part, we bootstrap the I/O construction for shallow circuits and get a full-blown construction for arbitrary circuits. In doing this, we rely on fully homomorphic encryption with shallow decryption circuits. And that's not a really strong requirement because all fully homomorphic encryption schemes that we know indeed satisfy this requirement. And the really nice thing is that this transformation is actually very simple and can be provably based on the underlying primitive. So I'll actually start with this simpler step of bootstrapping and then move to the more complicated step of realizing indistinguishability obfuscation for shallow circuits. Okay? Okay, so let me start with this bootstrapping. Okay, let me start by giving an overview of how this is going to work. The values in blue boxes are going to be in clear form. They are plain text. The values in red boxes are encrypted under some fully homomorphic, under the public key of some fully homomorphic encryption scheme. Okay. So what if I was to give F is the circuit that I want to obfuscate. If I was to encrypt this circuit and to give an encryption of this circuit, then given any value X in the plain form, you can easily compute F of X in the encrypted form. Okay, so fully homomorphic encryption allows us to do that. Given encrypted F and X in the plain text form, you can compute encrypted Fx. But obfuscation requires that this Fx be in a blue box. We want Fx to be in the plain text form, not in the encrypted form. How are we going to make that happen? We're going to give away, note that we have access to an obfuscation, an I/O for NC1 circuit. So we're going to give away an obfuscation for a conditional decryption circuit. So what this conditional decryption circuit does is that it actually it decrypts Fx and brings it to a blue box. Note that this, remember that this decryption circuit uses the secret key of the homomorphic encryption scheme. We'll need that later. Now, it cannot decrypt everything. If this conditional decryption circuit was actually decrypting everything, I could directly use it to decrypt F. But instead, I just wanted to decrypt values of the form fx, which have been computed using this fully homomorphic evaluation here. Okay. Now, in order to ensure that, we're going to have the conditional decryption operation verify that this computation was done correctly, and decrypt only if the computation was done correctly. Now, the good thing is that if you give this decryption circuit an if you give the decryption circuit an actual transcript of the evaluation going from f to f of x, then this verification can actually be done in polytime. Oh, there's a question by Daniel. To obfuscate a polynomial size function of size this, is the IO size poly f, poly, well, it's the size of the circuit, not the function. Besides that, everything is fine. Did I answer the question? Yes, it's poly f.
Yeah.
It's poly f. It's poly star, it's poly f, poly lambda. Okay. So it's just polynomial. We're not looking at polynomial in the security parameter and the size. I mean, we can get to it later. I'm not sure. I mean, I can think about it. I would have to check. I don't remember what exactly, but I'm pretty sure it's poly f into poly lambda. So it might be f into poly lambda, but I don't remember exactly. Anyway, let's get to this. This is not that important a point.
Sanjam, maybe feel free to ignore this. Maybe it's meaningless. But I'm just wondering: is there an issue here similar to circular security? The fact that the secret key both appears inside the thing you're trying to obfuscate, and also depends on what has to do with the input.
So you have asked the question that I'm just going to get to next.
Okay, sorry.
Okay. So this circuit decrypts. It verifies that the computation has been done correctly, which can be done in log depth, and then decrypts, which can also be done in log depth, and outputs f of x. Okay. Now, one question, as Oded asked, is that we have a secret key embedded in it, and what we don't have a perfect obfuscation. This is so we're going to obfuscate this, and our obfuscation is going to consist of an encryption of f and obfuscation of this conditional decryption circuit. But this decryption circuit had the secret key embedded in it, and we don't have perfect obfuscation. We only have like this weaker indistinguishability obfuscation notion. So what is possible is that the adversary could extract the secret key out and then use it to decrypt this f and get back f in the clear, which would be disastrous. Okay, is this the question that you were asking? I guess.
Yes.
Okay. So now, actually, the solution to this problem turns out to be fairly simple. The idea is to, instead of having just one copy of the fully homomorphic encryption, have two copies. So what I'm going to do is that I will give an encryption not just of one encryption of this f under one public key, or the red public key. I'm going to give another encryption of the same f under another independent public key for full homomorphic encryption. And this would allow you to compute f of x in the red and f of x in the yellow box. The conditional decryption circuit can verify both things. It can check whether the computation was done correctly and the yellow computation was done correctly. It decrypts only if the red computation if both the computations were done correctly. But observe that it doesn't matter whether the circuit has the first secret key or the second secret key. But regardless of whether the circuit has the red secret key or the yellow secret key, so our obfuscator is now going to be the red f, the yellow f, and the obfuscated the conditional obfuscation of the conditional decryption circuit. And you can't even tell whether whether I use the red secret key or the yellow secret key. Okay. So intuitively, what this means is if you can't even tell which secret key I'm using, you cannot figure out the secret key itself, and thereby you cannot figure out anything about the function. This argument can be made formal, but just want to make sure, is the intuition clear? Any questions?
Can you say again, how come you cannot tell which of the secret key you're using? Because I could modify one of the homomorphic encryptions and then see if you suddenly don't, stop accepting?
Yes. So this circuit actually checks that both evaluations were done correctly. It has the red F and the yellow F hard-coded in it.
Right.
So it has these values in it. It gets red FX and yellow FX as input, and it also gets as input the transcript of the evaluation. So it just checks that each step of the evaluation was done correctly. So if the fully homomorphic encryption had perfect evaluation and perfect decryption, then regardless of what these values were, and if the computation was done honestly, as is verified by the conditional, then the red ciphertext and the yellow ciphertext encrypt the same value, regardless of how you obtained it. So it doesn't matter whether you decrypt the first value or the second value, you get the same answer.
Okay, so in some sense, it's a bit like what you get in CCA security. Like you want to.
Yes, it's very similar. It's very similar to the FLS trick, going back where you can have two witnesses and you can't tell which witness is being used.
Okay.
Yeah.
Thanks.
Any other questions? Okay, so this is the more elegant part of the construction, and very simple actually. The more complicated part is what I'm going to describe next, and this is realizing the indistinguishable obfuscation construction for the NC1 circuits. This construction is going to proceed in roughly 4 steps. I'm going to start by viewing the NC1 circuit as a matrix branching program. I'll tell you what this matrix branching program looks like, and we will see that how it follows from branching program. I won't describe the details of the Barrington's theorem or how we get it, but I'll describe what a matrix branching program looks like. Then I will recall techniques that were introduced by Killian for randomizing these matrix branching programs, which achieved some nice properties. At this point, we will have we'll have some sort of a construction which is not secure, but we will have to restrict the kind of things. So we'll be giving adversary some things, but it can use those things to do something more than what it's allowed to do. So it would still be able to learn something intricate about the function. And so we will use multilinear maps to hide the computation, but there would still exist some attacks. I'll describe some of these attacks and the fixes that we have for them, and then I'll move on to the security of the scheme. Is the outline clear? Okay, let me start by describing what a matrix branching program looks like. So Barrington's theorem tells us that if you give me an NC1 circuit or a log depth circuit, then he can convert it into a poly-length matrix branching program. There's some small technicalities which I don't want to get into. I just want to tell you what I view as a matrix branching program. The fact that it can be gotten using Barrington's theorem is easy to see. So a matrix branching program looks like this. Okay, so consider, for example, a length 9 program with a 4-bit input. Okay, I'm denoting inputs and some of these matrices here by colors, and how the computation. So the description of the branching program consists of these 18 matrices. So if you give me a branching program, then you have to give me these 18 matrices. How the computation is done is as follows. I look at the first bit of the input, which is, I'm also going to call it the light green input. And I look at this first bit of the input and notice that this bit of the input affects these 3 steps of the branching program. It affects the 3rd step, the 6th step, and the 9th step. Let's say the first bit was 0. Then I choose the upper matrices among these matrices. Among these 6 matrices, I choose A30, A60, A90. Okay. Next, I look at the 2nd bit in a very similar fashion, which affects the dark green matrices. So I look, let's say this bit was 1, then I take the lower matrices. Okay. Next, I do the same for the gray color and for the red color, and I obtain basically a matrix for each. In each column, I have obtained 1 matrix. Okay. And how the computation is going to be done is that we're going to multiply these matrices that I have picked up using this mechanism, and I'm going to output 1 if the multiplication evaluates to identity matrix, and otherwise output 0. So is the evaluation clear? I want to make sure that the evaluation is clear, because if I move on, then it'll be difficult to understand what's going on.
The matrices, they're Boolean matrices, and you're doing multiplication over.
Yes, you can think of them as Boolean permutation matrices, and you're doing multiplication, just regular multiplication. Okay. And if the output is identity, you output 1, otherwise you output 0. Any other questions? Okay. Now Killian provided for a mechanism of randomizing these matrices, which achieved some nice properties. So let me tell you what properties he achieved. But before that, notice that if you wanted to evaluate this branching program on this input 0, 1, 1, 0, you don't need all the 18 matrices. You only need 9 matrices, like the ones that we chose before. So you could have thrown away the rest of the matrices and just multiplied them and achieved. Okay, this would give you the output. Now what Killian pointed out was that there exists a randomization strategy. Well, one thing is clear, that you can multiply them and get the output. Now Killian's point is that you can randomize these matrices in a way that the output is the only thing that you learn from these matrices. Okay, so if you randomize these matrices in a fashion, in a specific fashion that I'm going to describe next, then you can ensure that the only thing that someone can learn given these matrices is the output and nothing else. Is that point clear? I'm going to describe the randomization strategy, but I want to make sure that people understand what the goal here is. Okay, so how is the randomization going to work? The randomization works by sampling 8 random matrices. Now these matrices don't have to be Boolean, but these will be just, if you're sampling in some field FQ, and I'm requiring that these matrices be invertible. If they're not invertible, you can sample some other matrix. I'm going to sample 8 matrices, and I will describe how I'm going to randomize this specific matrix A50. I'll tell you how I can randomize this matrix. The randomization for all the other matrices is going to be done analogous. Okay? So how I'm going to randomize A50 is that I'm going to left multiply this matrix A50 with R4 inverse, and right multiply it with R5. Note that both of these are random matrices, and I'm just multiplying on both sides. Okay. Also note that the same randomization can be done for in a similar way for the rest of the matrices. For example, A30 will be left multiplied with A2 inverse, and right multiplied with R3. Left multiplied with R3 inverse, and right multiplied with R2 inverse, and right multiplied with R2. Except for the end matrices, which will not be left and right multiplied. So A11 will only be right multiplied, and A90 will only be left multiplied. Okay. After I do this computation, I get these matrices. Okay. So these are randomized matrices from the matrix branching program. It can be seen that you can still evaluate the same thing using these matrices. If you were to multiply these matrices, then at each intermediate level, the R inverse and the R will cancel out. So on B11 is right multiplied with R1 inverse, and B21 is left multiplied with R1. So the random matrices cancel out. Similarly, the random matrices between B21 and B30 cancel out. So the computation yields the same thing as was obtained by multiplying the A matrices. But what Killian argued was that this randomization hides everything else besides the output. Okay, so this should kind of, I'm not going to argue why this is the case, but this should intuitively be understandable, because all these matrices basically are random matrices subject to the constraint that their product is same as this answer. Okay. Okay. So once we have these random matrices, this is going to be the starting point for a construction. In our construction, instead of Killian only gave one of the matrices, we're going to randomize in the same fashion, but we're going to give both matrices for each position. Okay. If I was to give you just one matrix for each position, then Killian argued that nothing else was lost besides the output on that input. But if I give you all the matrices, then certainly perfect privacy is lost. You could learn many, many things about the computation. You can learn many, many things about the matrix branching program. Okay, is that clear? Okay, so our first step is going to be to hide what the adversary can do with these matrices. I mean, he can do arbitrary computation on them if you just give him directly, to make it hard for him to do arbitrary computation, but only allow him to multiply. We want to restrict him to sample 9 of these matrices and only multiply them and only check if the answer is identical. This is our final goal. And even though we give him all the matrices, the first step in doing so is going to be to encode these matrices in some fashion which hides what the values actually are. Okay, so this is a bit technical, so bear with me and please do ask questions if there are any. So let me tell you a little about multilinear maps. So multilinear maps are going to be the tool that we're going to use to encrypt these matrices. These are going to be encryptions, not satisfying the usual notion, but they're going to hide what the values are. But we will still have this property that you can check if a matrix, after you can multiply the matrices and you can check if the final thing is an identity matrix or not. Okay. So more formally, a cryptographic D-multilinear map is defined as follows. I give you groups G1 to GD of prime order P with generators G1 to GD respectively, with a target group GT and generator GT. And we require the existence of an efficient, so this should be like polynomial time map that takes an element from G1, G2, GD and outputs an element in GT. So for the cryptographers in the audience, I'm looking at the asymmetric multilinear map. And the multilinearity property says that if I was to pair G1 to the A1, G2 to the A2, and so on to GD to the AD, then what I get is in the target group, the multiplication of the exponents. In my construction, I want you to think of these A1 to, it's not exactly the case, but I want you to think of them as matrices. It'll be easier. So the matrices that I'm giving you, I'll just directly put them in the exponent. I'll show them in the next slide. One point I want to mention is that the multilinear maps that we had in GGH are actually noisy, but I want you to ignore that for a minute because that's not going to affect our construction. It only affects the technical details. Okay, so how are things going to be encoded? I had these matrices. Remember, these are the randomized matrices. I'm going to encode the BIBs. So I'm going to encode, for example, the fifth matrix, like these in the group GI-BIB. So I will put B50 as G5B50. Okay, is that clear what I'm doing?
This is entry-wise, yeah.
Yes. So it's entry-wise, but I want to because I want you to think about the pairing itself being done. Like if it was entry-wise, then when you multiply two matrices, then you also have to do additions and stuff like that, right? But I want you to think when the actual multiplication is done, it's all happening under the wraps. I don't want you to go think about the details. They're not important. Does that answer?
So you're saying that the multilinear maps allows you to multiply matrices?
Yes, yes.
Okay.
They allow you to do that, and that's not something to worry about. It makes it simpler to write and to explain that the entire thing is encoded as one big thing in the exponent rather than entry-wise. Even though when you actually do it, you will have to do things entry-wise.
And what about the order of the groups? Do I have to worry about that?
Yes. So the first entries will be in the first level. The second one in these ones will be in G1. So I have G1 to GD.
Right.
And D in my case is going to be 9. So B10 and B11 will be in G1. B20 and B21 will be in G2, and so on. And B90 and B91 will be in G9. Okay. I mean, this is represented by the subscript here.
But that's probably an issue just to choose it big enough, right? Because the matrices are 0, 1.
Well, I mean, the randomization is not. The matrices are 0, 1, but the randomization is not.
I thought randomization is. Oh, I thought it's all done in the group S5 or something like that.
Yes, for Killian it was enough, but for our case, I mentioned that we're going to randomize with arbitrary, in let's say ZP star.
Okay.
Any other questions? Okay, so once we do this encryption, what we're basically doing is these matrices are now colored differently. For the rest of the talk, I'll still use the previous colors, but you can think of them as having changed colors. They're now under the wrap. The computation you can do is only kind of multiply. You can, in each column, you can only pick one matrix. You can multiply them together, and you can check if the answer is identity. You can do nothing else. Okay. Okay. So there are still attacks, and I want you to see these attacks. So there are still some attacks that remain. And the attacks, I'm going to give two examples of attacks here. The first one I call is a mixed input attack. Okay, it's actually very easy to see. Note that honest evaluation on any input, for example, if the dark green bit of the input is 1, requires that you choose B21, B41, and B71. Is that clear? Just from the description of how matrix branching programs were evaluated, you must choose these 3. Right? Now, if I was to give these values to the adversary, nothing stops him from choosing B21, B71, but instead of B41, choosing B40. Note that if he does this computation, the right matrix on the randomizations would still cancel out, and he would still be able to multiply these matrices. Okay? What this is intuitively allowing the adversary to do is that he learns something about the circuit that he shouldn't have learned. More specifically, if one input wire is going at 2 different places, he's fixing different inputs for the same input wire at 2 different places. So he's able to do something with the circuit that might allow him to learn something more than what we want him to learn. Is the attack clear? Any questions? Okay, the second attack that I want to talk about is the attack of partial evaluation attack. So what's happening here is, imagine, so I have a blue box and a red box. Okay, the adversary might just multiply the matrices B50, B60, B70, B80, and multiply the matrices B51, B60, B70, B80, and compare the 2 answers. Okay, so more formally, what he's trying to do is evaluating the circuit on 2 different inputs, okay, only partially, and looking at some internal wire of the circuit. Now, if the 2 values are identical, if you multiply B50, B60, B70, B80, and you multiply separately B51, B60, B70, B80, and the answers are same, so you can subtract them and check if the answer is 0, then this allows you to figure out an internal wire of the circuit. Okay. So I'm evaluating the circuit on 2 different inputs, and I'm learning a specific input wire, and I'm seeing if on those 2 different inputs, an internal wire of the circuit computes to the same value. Is it getting technical? Well, please feel free to ask questions.
Actually, a stupid question then. Did you already use the fact that you randomize using Killian?
Yes,
you're
yes.
encrypting it, okay?
We have both Killian's randomization here, as well as multilinear maps.
Right. Where do you use the fact that you use Killian randomization?
I'm describing the attack. So this is not the Killian's was guaranteeing that if you chose one matrix at each step and multiplied them, right, then you would get something that was that would hide everything except the evaluation of the program on that specific input. But now I'm giving you both the matrices, so you're definitely learning more, and I'm giving examples of things that you're learning more even after I put multilinear maps in.
Okay, I guess I meant to ask if where is it used in security, but we might see it later. Right? You haven't discussed that yet in the proof of security. The fact that Killian is there, or it's already obvious.
Well, I mean, the Killian's. Let me go back and mention. Okay. So Killian's point was only that, you know, if I give you just these matrices, then security is perfect. There's perfect security because these matrices are completely randomized.
But when you have it's encrypted anyway, right? So it should be you have it encrypted, right? You don't really provide the matrices.
Yes, but this is not a regular encryption scheme, right? We're encrypting under multilinear maps, which allows you to still do some operations with these matrices.
Right. Good, good. So you did perfect security that Kilian gives you for that setup, where you only choose one of the two.
Yes.
And for the other stuff, you have to use the multilinear. Okay.
So now we have these randomized matrices, and then we do a multilinear map on top of it.
Sure.
And I'm saying still there are attacks.
Yeah, thanks.
Okay. And those are these are the attacks that I just described. The first being mixed input attack, in the sense that nothing stops you from choosing for the same input bit different matrices at different steps of the branching program. So, for example, you could choose B21, B71, and B40. Okay. Any other questions on it? I'm happy to, like, even if you feel like there's, if you have a comment, please feel free to say. Okay. I'll move on to the second attack, where I said what you could do is you could do this partial multiplication, where you could do this partial computation where you're only multiplying the things in the blue box or the things in the red box, and then you're checking. So look, these things are encrypted under multilinear maps, but the fact that I have it's a multilinear map allows you to, these are not perfect encryption. They still allow you to check if they compute the same value. Okay, so you can still check that, and what this is allowing you to do is allowing you to say something about the internal wires of the circuit. Okay, so the first attack allowed you to fix a particular wire of the circuit to a value of your choice, even though you shouldn't have been able to. This attack is allowing you to look at probe internal wires of the circuit. Both the things are contrary to what obfuscation should give you. Make sense? Okay, now let's get to how we solve these solutions. So I'm going to start by giving examples of ad hoc looking solutions, but which actually end up solving the entire problem. So for both problems, I will give you, for both the attacks, I'll give you a solution for the problem, and when you will put the two solutions together, what we end up getting is something that's that can actually be argued to be secure. Okay, so recall the first attack was that the adversary can can mix and match. Our strategy to prevent mix and match is going to be to use a technique of multiplicative bundling. So what I'm going to do is that I'm going to multiply B20, B40, and B70 with alpha 1, alpha 2, alpha 3 respectively, and B21, B41, and B71 with beta 1, beta 2, beta 3 respectively. These are just random numbers in the same space from which your randomizers were coming, and I'm just multiplying them with these matrices. And the additional constraint is that if you were to multiply alpha 1, alpha 2, alpha 3, and beta 1, beta 2, beta 3, both values should be equal to 1. Okay. Now, can you think about the attack that we were trying to launch? The attack was where you were using B21, B40, B71. Can you see why this attack goes away with this multiplicative bundling?
So your output is going to be multiplied by a random scalar.
Yes, exactly. So if I was to take these matrices B21, B40, B71, then the output is going to be multiplied by beta 1, alpha 2, beta 3, which is just a random scalar. Okay. So what we achieved was we made it the adversary can no longer get anything meaningful by multiplying these inputs inconsistently.
Should we think of the finite field as being of super polynomial order?
Can you repeat your question?
I mean, the scalars are chosen from a certain finite field, I imagine. So
yes.
Modulus
So,
of P.
Yeah, think of ZP star.
Right. Should I think of P as being polynomial or super polynomial?
It's super polynomial.
Right. Otherwise, there'll be noticeable probability.
Yes. Otherwise, there will be a problem. Yes. Yes.
Sure. That's right.
You can think of even exponential. So this goes to the question you're asking. Actually, kind of touches upon the details of the multilinear map, and there you can have these of exponential size. So you can make these randomizers come from an exponential size space. Okay.
So the key thing is that in multilinear maps you can test identity, and if it's not identity, you get no information. So that's
Yes.
the idea here.
Yeah.
Okay.
Yes, yes. You can also check if two things are equal. So identity is a special case.
The same. Yeah. Sure.
Yeah, yeah. Okay. So I describe this randomization only for the dark green matrices. You can do it for every other color as well. So you will have a randomization that's done for the gray color and the randomization that's done for the light green color. Trying to do the randomization for the red color brings me to my second attack. Okay. My second attack was if I was trying to do evaluation, this partial evaluation with the blue box and the red box. What I was doing was I was multiplying B50, B60, B70, B80, and separately I was multiplying B51, B60, B70, B80. And I was comparing the two. Now observe that what will the randomizers in the multiplicative bundling have to be for B50 and B51? They will have to be both 1, right? Because there's only one occurrence of this matrix. The only way you can sample these random values here such that the product is 1 is by sampling all of them to be 1. Okay? Is that clear? So to solve this problem, we're going to have a kind of a second order of multiplicative bundling, which I call the extended multiplicative bundling. And how this is going to work, it is in principle very similar to the first technique, but goes a step ahead. So the idea is that I am going to multiply all the upper matrices with random multiples of gamma 1, gamma 2, gamma 3, gamma 4, gamma 5, gamma 6, gamma 7, gamma 8, gamma 9. And similarly, the lower ones with delta 1s, delta 2, delta 9. Okay. Now, of course, if you were to multiply B50, B60, B70, B80, and the B51, B60, B70, B80, you will get different values, because in the term corresponding to the blue box, you have in the product gamma 8, gamma 7, gamma 6, gamma 5, but for the red box, you get instead of gamma 5, delta 5. Okay, so you still have different random scalars. But note that we have already also introduced a problem here. Can you see the problem?
Sure. I mean, you need to ensure that when you take your alternating kind of multiplication that's allowed, you get 1, right? So
Yes.
It seems like there's a lot of conditions you have.
Yes. So the solution to this problem is actually pretty trivial. What we're going to do is we're going to have a shadow version of the same scheme, but and the same randomizer, but instead of these matrices B, we're going to have identity matrices. Okay. So what we're going to do, you're still going to, in the regular scheme, you're going to still multiply things in the same way, but you will get a weird gamma delta combination. Now, in order to check whether the thing is an identity matrix, you multiply the same order here and check if the values are the same. So for example, if you were trying to evaluate the program on all 0 input, what will you be doing? You will be multiplying all these matrices. Can you see the pointer on which the pointer is moving?
Yes.
So you will be multiplying these matrices, and what you will get is you will get a multiplication of all the gammas in the product, right? Now, in order to check if you got the right gamma, I have a shadow version of the scheme where instead of these matrices B, I have identity matrices multiplied with the same constants. So if you were to multiply all the 0 matrices in the shadow scheme, you will get the same constant. At which point you can check if the two constants are equal.
So with the shadow thing uses different Killian randomizers than the original.
Yes,
right?
the Killian randomization. So these are identity matrices with some randomization. The Killian re-randomization could potentially be different here. That has no correlation. Only the gammas need to be the same, and the deltas.
The groups are also different. You have 18 groups now, or?
No. Well, I mean, this is the same groups. So this will again be in G1, G2, G3, G4. It's the same group. That's the most simple way to think about it. You can have more complicated things, but I don't want to go there. Does that make sense?
Yes, thanks.
Okay, so this is a sort of multiplicative bundling, but here, so what's happening is for every input that you pick for which you're trying to evaluate the branching program, there exists a unique constant that will be attached once you evaluate when you multiply the matrices together. So there's a unique constant that exists, and the only way to check if there's a shadow version of the scheme which allows you to evaluate the same constant, and then you can compare and if the values are same. So this prevents all kinds of partial evaluation attacks. Okay. Any other questions? I'm happy to give a minute or two if people want to think about it.
Do you have issues with reordering?
Ordering in terms. Oh, so that's taken care of because of the randomizers, right?
Oh, okay.
Yes, the randomizers ensure that you can multiply only in order.
So is that the only place you're using Killian's randomizer?
Well, it's difficult to say what is the only place where something is being used, because everything is very intertwined, and but very explicitly that is the main purpose that Killian's randomizers are serving.
I mean, at the basic level, they also hide the individual matrices, right? If
Yes.
you didn't,
Yes.
that
Yes.
is
I mean, it's doing a little more, right? Because if you were just, it's doing significantly more, because you're also hiding the matrices in some sense by those randomizers. You're not just making sure that they multiply in the right order, but you're hiding the values themselves. So this is a kind of at an intuitive level. It's hard to say what part is explicitly preventing. I mean, you can say this attack is prevented by this thing and this thing. So it's hard to say what purpose it is not serving without having explicit attack in mind. Okay. Okay. So let me move on to say a few, at least something about the security of the scheme. So the construction as we have seems robust enough to attacks. And we can cast it as an assumption. This is not a standard assumption, and it's a complex new assumption, but we provide evidence that for the security of this construction by giving a proof of security in a certain generic multilinear matrix model. So this is analogous to, for the cryptographers who are listening, this is analogous to the generic group model in the bind linear setting that people often consider. And this evidence has been further strengthened by follow-up works by Berkersky and Rothblum, and Barak, myself, Kalai, Panit, and Sahai, where we get schemes which are very similar to the construction that I just described with some tweaks, but where the security can be based on generic multilinear model. So in the construction that I described to you, I was thinking of these entities as matrices. If you were to open up the matrix and look at each individual term separately, it's opening a can of worms, and there could potentially be many other attacks that we could think about. But as it turns out, that can of worms is not really problematic. It's problematic to argue it formally, but it's not problematic in terms of actually having real attacks. And then the argument can be, a strengthened argument can be given in those settings. Finally, I'd like to mention about the open problems. Really, I think the most important problem here is to get our notion of obfuscation, indistinguishable obfuscation, realize this notion under better assumptions. Another really important problem is to explore what's the limit of strengthened notions which you can reach. So this relates to Oded's question about how is it weaker than virtual black box? That we clearly know, but is there a fine line that we can draw as saying that these are the classes of functions for which we can achieve VBB, and these are the functions for which we cannot? Definitely a lot more needs to be done on getting faster constructions. If you thought that fully homomorphic encryption was inefficient, then obfuscation is certainly from a different planet. With respect to applications, as I mentioned before, I think that obfuscation is a primitive that can touch upon potentially every application that we have in cryptography. So pick your favorite application and try to see if obfuscation has some implication for that application. Thank you. Any questions?
Okay, thank you, Sanjam.
Thanks a lot.
Any other questions? I see a question.
Can you hear me?
Yes.
I was wondering whether you proved that your scheme is secure under those two attacks that you had shown, or under any possible attack.
So that's what I said. So it's secure in the generic model, which is it's secure against all possible attacks in this generic model. So what I mean by that is, as long as you don't question the security of the multilinear maps, you're not looking you're not looking at the bit representation of the of how the encryptions are done. There are no attacks. If you start looking at the bit representations, then it becomes more complicated. At that point, you have to study the security of the multilinear maps, which is a totally different question than studying the security of the obfuscation. Does it answer your question?
Yes.
Okay.
One quick question. How difficult is it to get the decryption circuit in NC1 for the fully homomorphic encryption? Or is it's already known? It's easy?
So all known FHE schemes trivially have their decryption circuits in NC1.
Good. Okay, thanks.
Any other question?
There's a question from
The
any
UMD group seems to have a question. I'm not sure. Okay.
Daniel has a question. I think we can make sense of it. So he asks, can you please explain the relationship between them? I'm not sure what them is.
Between them?
Yeah, he says between them.
Yeah.
Daniel, do you care to explain? Sorry, it's not Daniel. Someone's typing.
Yes, I'm seeing. Yeah.
Oh.
White box crypto, I'm not completely familiar with the formal notion of this term. Can you guys explain? And
So maybe in the meantime you can. So maybe in the meantime you can just elaborate a bit more on the issue of assumptions. Like imagine one day you construct multilinear maps based on the standard assumption, like
yes.
LWE or something like that. And
yes.
so why doesn't it immediately also imply security for your obfuscation? I'm just trying to see why is it such a subtle security?
So the thing is, it's like saying, I think I can explain it well with respect to the bilinear setting. So there are many different assumptions in the bilinear world, right? The bilinear Diffie-Hellman assumption. Then there are these Q-type assumptions where the assumption consists of many group elements and stuff like that. So all these assumptions are equally. I mean, some assumptions people might believe more. Some assumptions other people might believe less. But we have no explicit reason to believe why one assumption is better than the other, right? So if we have multilinear maps from LWE, we are in a similar situation. If you have an assumption from LWE, are you proving multilinear Diffie-Hellman assumption, or you're proving some other assumption? What we have for obfuscation is some other assumption which is more complicated than the multilinear Diffie-Hellman assumption. Does it make sense?
So you say the construction is not just using the multilinear as a black box. Is this what you say? You're actually using the internals of the multilinear construction? Redoing it?
I think you're mixing two things. One is using the construction. Well, if you had multilinear maps in a completely perfect multilinear maps under LWE, and it was known that every assumption that was realizable, that was generically provable in the multilinear setting would be true, then yes, you could have instantiation here. But it's not the case. Proving different assumptions in the multilinear setting is a different setting, right? Proving one assumption is different from proving the other. This is cleanly observed in the bilinear world, where we have a decisional linear assumption, multilinear, bilinear decisional Diffie-Hellman assumption, and these inversion assumptions, and all these assumptions, they all seem believable, but they're all different assumptions. They don't imply each other. So it's not clear that if you had multilinear Diffie-Hellman assumption from LWE, that would imply this assumption. But there's no reason either to believe that this assumption would be weaker, it should be more difficult to break or something like that, or easy to break.
Okay, thanks. Any other questions? Okay, so let me just thank again everyone for joining, especially those for which it's almost 10 p.m. Or later. If you plan on joining again, let us know so we can try to schedule it a bit differently in the spring. And again, in 2 weeks, we'll have David Stoyer. Any other question before we slowly go offline? Thomas, anything else to add?
I have one last question. You said that at some point at the end, you said that you have some evidence that your new assumption.
I just
Hello?
If you click on it, it changes the.
Okay.
Can you hear me?
Yes.
Yeah. So you have this new complex assumption,
Yes.
and you made a remark that there is, in some sense, you are giving some kind of evidence that this complex assumption is really a difficult problem.
Yes.
What is that evidence?
So this is the evidence of giving. So there are two kinds of. So let's break things into two parts. One is what I'm going to call generic attacks, and the other are called non-generic attacks. So generic attacks don't, for example, if you were thinking of discrete log, will only try to look at group elements directly and perform these operations directly. The non-generic attacks will start to look at the bit representation, and then you can start looking at attacks like index calculus and stuff like that.
Mm-hmm.
We show that there are no generic attacks. Okay, we have a proof saying that there are no generic attacks. For the non-generic attacks, there was evidence in the multilinear maps paper. We looked at a very wide range of or whatever is known in terms of non-generic attacks for lattice-based constructions, for ideal lattices, and explicitly extended them. Some of those attacks could be extended in our setting, and even after those extensions, our scheme could not be broken. So we looked at all the attacks that exist in the literature, extended them for the non-generic setting, extended them, and still they're not applicable for our construction.
Okay, so basically you are not able to extend the known non-generic attacks to attack this particular scheme.
Yes.
Okay.
That's for the non-generic attacks. For the generic attacks, there is a proof.
Okay.
Yes,
okay.
That there is no generic attack. Yeah.
Okay. Yeah. Okay, so those of you who wish to stay, you can stay. Let's this point go offline, and you're welcome to stay and ask more questions. So thanks everyone for joining.